So, having looked at Blackboard ahead of time, right? What are we covering this week? No, I'm not being sarcastic. I mean,
A series of parallel circuits.
yeah, thank you. He gets a gold star like everybody else. So the good thing in this class is it's largely review of these first couple weeks. And that's because I need to make sure you have everything down foundationally from last semester. We don't want to get 4 weeks in and realize that you have things missing. So what I want to do is review a series and a parallel circuit. This week's lab is that you go through and you do all the theoretical work, the homework on these. I mean, like you would do the homework by hand. And then you build it and you measure everything that you build and you make sure you get the same results out of both and compare them. You've done this before, so this is mostly make sure that anything we forgot over winter break we've got back, and make sure that anything we're kind of still missing we've got down. So if you did really well in the fall, hopefully you just come in, just get it done, get out of here. So, which you want to do first, series or parallel? Do you care? Series circuits. Right. I'm going to give myself a 12-volt battery. I'm going to connect it to 3 resistors in series. I'm going to call these resistors R1, R2, R3. I'm going to give values 820 ohms, 1 kilo ohm, and 1.2 kilo ohms. So common real-world resistor values. Then we're going to build our table over here. We want to list the battery, R1, R2, R3. We want to find the voltage and the current and the power for each. So we'll come do that work here in a second. Before we do that, I'm going to go over to the other board. So for series circuits, tell me everything you recall about series circuits. The big highlights, what's important? All series circuits have the same current, yes. Same current through everything. Whatever charge flows out of the battery, the current, is going to flow into R1, and that charge has nowhere to go but to flow out of R1 and R2, and nowhere to go but to flow out of R2 and R3, and then back to the battery. That's true of all series circuits. It doesn't matter if they're resistors or diodes or capacitors or transistors or whatever. Everything in series has the same current. All right. Voltages, I'm going to write it this way, sum to 0. And by that, I mean I gain voltage, I'll put polarity. So I'm going from negative to positive, right? I'm gaining voltage as I go up. As I go across resistor 1, I'm going to drop voltage. As I go across resistor 2, I'm going to drop voltage. If I go across resistor 3, I'm going to drop voltage. I'm going to call this V1, V2, V3. Those are the voltages across those 3 resistors. Those 3 voltages would add to be the same number as this, but this is a gain and those are drops. So really it's this minus this minus this minus this is 0. So if I go around here, all the voltages need to total to 0 when I go around to the same spot. Or if you want to think of it this way, all the voltage in by the battery has to equal all the voltage out by the resistors. What about the resistors? The total resistance is R1 plus R2 plus R3. I'm going to put dot, dot, dot. Obviously, I only have 3 resistors here, but in a general case, the resistors all sum. Last thing I want to check is, I'm going to say the power in equals the power out. By that I mean all the power put in by the battery equals all the power dissipated by the resistors. So when I calculate power here, the power that the batteries put it in should equal the sum of those three. So with that, and I would encourage you, again, to work these with me. Bring calculators, have calculators out, be ready to work. Remind somebody again of my analogy the other day of like sports, right? Watching me put stuff in my calculator is like watching the coach do the drill. So I have current that's going to flow this direction, and I have one current for the entire circuit because it's series. That's what we just said. So I know my current equals the voltage over the resistance. Which voltage? Or the battery voltage over the total resistance. If I want to think of it this way, I have an equivalent circuit that is 12 volts and a single resistor. What is that resistor value? Well, it's R1 plus R2 plus R3. So it's 820 ohms plus 1 kilo ohm. I want to make sure these are all the same. So 1 kilo ohm is 1,000 ohms plus 1.2 kilo ohms is 1,200 ohms. So our review hits multiple things here, right? Make sure we have all our conversions. So 820 ohms plus 1,000 ohms plus 1,200 ohms is 3,020 ohms. So now I can find that current. You guys are going to have to know and let me know how this red shows up on this recorded bit. I like to solve with a different color, but if you can't read it, let me know. 12 volts over 3,020 ohms equals 0.0039735 amps. So I'm going to move my decimal spot 3, right? 1, 2, 3, and write that as 3.97 milliamps. So my current out of my battery is 3.97 milliamps. My current into R1 is 3.97 milliamps. My current into R2 is 3.97 milliamps. Current R3, same number. Series circuit, they're all the same. My battery. Better get the voltage right for that, 12 volts. Okay, if there are any questions about this, ask me now because we want to make sure we have this down. This is our starting point for the semester. Okay, let's do the voltages now. What's my voltages through R1, R2, R3? So voltage across R1 is going to be the current through R1. Right? We're just using Ohm's law over and over. It's the only thing is making sure we have the right values. So that's going to be my 3.97 milliamps times 820 ohms. Be careful. You got to get these in the right units. I mean the right multiplier. But anyhow, so 3.97 times 10 to the minus 3 times 820 gives me 3.26 volts. If you multiply 3.97 times 820, you get 3,207 volts. You should realize that's an error because I only have a 12 volt battery. times R2, 3.97 milliamps. And I'm gonna just go right as 1 kilo ohm. That one I can do in my head. 3.97 volts. My last one, 3.97 milliamps times 1.2 kilo ohms. .76 volts. Are we doing on good? Okay. Yeah, that red might be really tough to read. I love it conceptually to do different colors, but maybe not. Try the other red for power and see if that works any better. All right, now I'm going to get the power. Let's put a little block up here. Power in the battery. Power is current times the voltage. 3.97 milliamps times 12 volts. Now in this case, I mean, you could certainly go 3.97 times 10 to the minus 3 times 12 and get it adjusted. You only have one prefix. If you just took 3.97 multiplied by 12, you get 47.64. And you would go, but I use milliamps, so I get milliwatts out. It works as long as you only have one of those prefixes. Then you're multiplying. So let's go through and do this for each of the resistors. So I'll take my current, 3.97 milliamps, times 820 ohms. And I will get 3.26 milliwatts. I'll do 3.97 milliamps times, oops, what am I doing there? Not times resistor, times voltage. All right, 3.26 volts. I was like, that seemed wrong. Current times voltage. All right, so 3.97 milliamps times 3.26 volts is 12.94 milliwatts. For R2, 3.97 volts times 3.97 milliamps. .76 milliwatts. Finally, R3, 3.97 milliamps times 4.76 volts. .897, so 90. So I'm just going to copy those over here now. 12.94 milliwatts, 15.76 milliwatts, 18.90. I'm going to do my checks real quick. So these three voltages, 3.26 volts plus 3.97 volts plus 4.76 volts. The three voltages across the resistors, if I add those together, I get 11.99 volts. 12 volts. So these should add up to be this. Only for a series circuit. Power, 12.94 milliwatts dissipated across R1, 15.76 milliwatts on R2, 18.9 on R3. Add those up, I get 47.6. 47.64. So, all my dissipated power should always equal all my power in. That's for every circuit, actually. Series circuit, all my voltages on my resistors, or on my passive devices, resistors here should sum to be my total. Same currents. So if you can do this, you're good. So this week's lab and this week's homework are pretty much go back and do these kinds of things and just get them all right, get your free points. Not really free, but it's just making sure that if there's any little things that we need to get that we need to get nailed down before we move on, got it.